There's a particular kind of quiet that settles right before something stops. Not silence exactly, more like the moment a machine runs out of the thing it was running on. No dramatic winding down, no visible sign, just a change in what's happening inside, while the outside keeps going for a while, as though it hasn't heard yet. That's roughly where we're starting tonight. I want to be upfront about something before we get too far in. This chapter isn't really about a supernova. Not yet. It's about the long, unremarkable period before one. The build-up that doesn't look like a build-up. The part that, if you're watching from a distance of, say, 1,000 light years, you would miss entirely. You'd see a star, a big one, burning the way stars burn, and you'd have no way of knowing that somewhere inside it, a particular kind of ending had already been decided. The ceiling fan in this room makes a faint clicking sound on every third rotation. I've never fixed it. I've just gotten used to it as a kind of background metronome. I mention it only because there's something about that rhythm. The two normal rotations and then the slightly off one that feels like the right texture for what I'm trying to describe tonight. Most of it unremarkable, and then, but let's not get ahead of ourselves. A star that will eventually collapse isn't doing anything wrong. That needs to be said plainly, because the word collapse carries connotations it hasn't earned here. The star is doing exactly what stars do, it's fusing. Hydrogen into helium at the start over millions of years, and then, when the hydrogen in the core runs thin, it adjusts. It starts burning helium, and when the helium runs low, it adjusts again. Carbon, neon, oxygen, silicon. Each fuel source different, each one burning faster and hotter than the last. And each one producing something the star then has to figure out what to do with. The star doesn't choose these fuels sequentially out of preference. It's not reaching for the next thing. It's doing the only thing that keeps it stable, generating enough outward pressure to balance the gravity trying to pull everything inward. That tension between the star's own weight and the energy pushing back against it is the entire game. Every star that's ever existed has been playing it. Most of them play it for billions of years. Massive stars, though, the ones we're talking about, the ones 8 times the mass of the Sun and larger, they play it faster, much faster. And with more material, more gravity, more pressure, more heat, the game accelerates through its stages in what amounts to, on a cosmic scale, a kind of hurry. Silicon burning, the last stage, doesn't last thousands of years. It lasts days. So by the time we arrive at what we're actually here to look at tonight, the star has already spent most of its life. It's moved through fuel after fuel, and each stage has left behind a residue, the ash of whatever was burning, that settles into the core. The core grows. Slowly at first, then less slowly. What it's growing into is iron. Iron is, and I want to choose the right word here, iron is stubborn in a way that's almost rude, not unstable, not reactive in any useful way, just done. From the perspective of nuclear fusion, iron is the wall at the end of the corridor. Every element lighter than iron releases energy when you fuse it. That's the whole trick of stellar burning. Smash lighter nuclei together, get heavier ones, and the leftover energy is what holds the star up. But iron? Iron is at the bottom of a particular energy valley. Fusing iron doesn't release energy, it absorbs it. The star has been, in a sense, working towards this material for millions of years without knowing it was building something it couldn't use. And yet the core keeps growing. The star is still burning silicon in the shells surrounding the core. New iron is still being produced and falling inward, settling, adding to the mass. The core doesn't stop accumulating just because it stopped being useful. Gravity doesn't make distinctions. It doesn't look at iron and say, right, that's spent, we'll leave it alone. It just keeps pulling. The iron core at this stage is roughly the size of Earth, maybe a little larger. Packed into that volume is something like 1.2 to 1.4 times the mass of the Sun. It's supported for now, not by fusion energy. There is no fusion energy anymore, but by something called electron degeneracy pressure, which is a phrase that sounds more complicated than the idea behind it. Electrons are resisting being compressed. Quantum mechanics says they can only be packed so far before they push back, and right now that push is what's keeping the core from collapsing. It's not a comfortable arrangement, it's not built to last. It's more like something bracing itself. There's a threshold. There's always a threshold in these stories, but this one is precise enough that it has a name. The Chandrasekhar limit. Around 1.4 solar masses. When the iron core approaches this number, electron degeneracy pressure stops being sufficient. It's not that the electrons give up, they're still there, still obeying the same quantum rules. It's that the gravity has become so heavy, so relentlessly concentrated, that the rules stop being enough. I used to think about this as a kind of breaking point, a moment of failure. But I've since decided, or started to decide anyway, that failure isn't quite what's happening. The physics isn't failing, it's just reaching the edge of what it could handle given the mass it was asked to support. Electron degeneracy pressure was doing a real job. It held the core stable for a while, maybe weeks or months, maybe longer, depending on the star. And then the core grew past what the job description covered. Is there something worth sitting with in that? The idea that the physics didn't fail, that it just ran out of domain? Maybe, I'm not sure. What the core looks like at this point, if you could somehow stand near it, which you could not, for reasons that would disassemble you at the atomic level, is an enormous dense sphere of iron nuclei, electrons moving through them, heat measured in billions of degrees, pressure almost too large to hold a number for. It is not quiet, it is not peaceful, but from the outside, from the surface of the star, nothing yet reveals what's happening. The star still shines. The light we would see from it is still photons that left the outer layers, carrying heat from fusion that happened in the outer shells, completely unaware of the iron problem several 100,000 kilometers inward. Light from the surface of the star takes maybe a few hours to reach us at 1,000 light years. But the information about what the core is doing would take, well, it wouldn't reach the surface in any meaningful way. Not as light, not yet. The star keeps shining while its core sits at the edge of something. This is the part that gets me, honestly. The gap between interior state and exterior appearance. The idea that an object can be, in some fundamental sense, already past the point of no return, while still presenting to the universe as a normal functioning star. Billions of years of nuclear burning, 100,000 years of shell fusion, weeks of silicon burning, and now days, maybe hours, while the iron core grows incrementally, quietly toward a number. 1.4 solar masses, give or take. There's no countdown, no signal. Nothing changes in the star's light curve to tell you it's happening, or if there are changes, they're subtle enough that we've had trouble finding them, even knowing what to look for. The star does not announce itself, doesn't brighten unusually or pulse in a new way, it just keeps going, while inside the margin gets thinner. There's a detail about the iron core in these final hours that I keep coming back to. At these temperatures, 10 billion degrees and climbing, the photons bouncing around inside the core are energetic enough to do something they almost never do. They start breaking iron nuclei apart. Photodisintegration, it's called, and the word is almost too clean for what it describes. The radiation field, which was always just light-like energy bouncing around, has become hot enough to reverse fusion, to undo, in small amounts, the structural work of nuclear burning. All that iron, produced over millions of years of stellar processing, and now, in the last hours of the core's stability, the heat is starting to eat it. Not quickly, not all at once, but enough to matter, because photodisintegration absorbs energy. Energy that was holding things up. The core loses some of what it needed to maintain itself, and the gravity doesn't compensate. It doesn't give back. The pressure drops a little more, the core gets a little denser, the photons get a little more energetic, and the photodisintegration accelerates. This is the part that really gets going, this feedback, this tightening loop where each small collapse makes the next small collapse more likely. And then something else begins. The electrons, the ones providing degeneracy pressure, the ones holding the core up, start to be absorbed by protons in the iron nuclei. Electron capture. The protons take them in and become neutrons, and in doing so release neutrinos. Tiny, nearly massless particles that barely interact with anything. They stream outward through the core, through the star, and out into space. And with each electron that disappears, the degeneracy pressure drops a little more. The core was already being held up by something insufficient. Now the thing that was insufficient is being dismantled piece by piece, particle by particle, in billions of tiny reactions happening simultaneously across the entire volume of a sphere the size of a planet. The core doesn't know it's about to collapse, the electrons don't know they're being removed, the neutrinos don't know they're taking the last support with them as they go. This is where I want to stop for a moment, because I think it's easy to read through all this and feel like we're building toward the explosion, toward the drama of the supernova, and miss that what we've actually been doing is watching something quietly, irreversibly disassemble. The explosion comes later. It comes from the collapse. But the collapse itself isn't dramatic, not yet. It's slow by stellar standards and fast by human ones, and it is, in its way, the least theatrical thing you could imagine for an object this size. A core that has spent millions of years accumulating mass, arriving at a number, an arrangement of particles that held for as long as the physics allowed, and then an edge, crossed without ceremony, and whatever comes next. The star above it still burning, the light still travelling outward, the photons crossing space that have no way of knowing what just started below them. There is a particular image from nuclear physics research, not from a star, obviously, but from laboratory work on nuclear matter, where you can see the binding energy per nucleon plotted against atomic mass number. It's a curve, all the elements arrayed by how tightly their nuclei hold together, and right at the bottom of that curve, right at the lowest point, sits iron. Nickel sits very close. But iron is what we think of. The curve slopes down on either side. Everything lighter than iron can release energy by fusing toward it. Everything heavier than iron can release energy by splitting away from it. Iron is the bottom, the floor. Stars spend their lives falling towards that floor, fuel stage by fuel stage. And when they reach it, when the core is iron all the way through, there's nowhere left to fall toward, energetically speaking. The star has arrived at the end of what fusion can give it. It's not a violent place, that floor. It's just final. Quiet in the way that endings can be quiet when they've been long time coming. The silicon shell around the iron core is still burning, still adding to the mass. A matter of hours now, maybe less. The core is close to the Chandrasekhar limit, and the electron capture is ongoing, and the photo disintegration is ongoing, and none of it announces itself. The surface of the star continues to radiate. The outer layers are still fusing hydrogen and helium in their own shells, completely removed from whatever is about to happen at the centre. The star is, in a sense, several different objects at once, each layer running its own process, each one mostly unaware of the others. A kind of fragmentation that's always been there, built into the structure of massive stars, but that becomes almost strange to think about right now. The core tightens, the electrons thin out, the neutrinos stream away, something that has been waiting, though waiting is not quite the right word because it implies intent, and there is no intent here, just physics running its course. Something that has been approaching since the first iron nucleus settled into the core is now very close. We'll get to what happens next, the collapse itself, the bounce, all of it. But tonight I wanted to stay here for a while in the part of the story that usually gets compressed into a sentence or two before the event everyone actually came to see, the long accumulation, the stubborn quiet of an iron core sitting at the edge of something it has no way to prevent. There's something worth holding, not as a metaphor, just as a fact, in the idea that the most energetic events the universe produces begin not with violence, but with arithmetic. A number approached slowly, a threshold crossed without noise. The star doesn't know what it's about to do. If this kind of slow, unhurried science is something you find yourself coming back to, this is a self-funded project. A small team of 3 trying to make something worth your time. If you'd like to help keep it going, you can find us on Patreon. The link is in the description, and if you're already there, Matthew M. and Brian Winter, your support has been a kind of ballast for this whole thing, and I mean that. Alison, you've been here longer than almost anyone, and that quiet continuity means more than I usually know how to say. To every other Patreon member showing up for this, genuinely thank you. The outer core doesn't get a warning. That's the first thing. There's no signal that travels it up from the collapsing inner core to tell the layers above what's happening. Sound, pressure waves, the kind of information that matter passes to adjacent matter, moves at roughly a few thousand kilometers per second inside a stellar core under these conditions. Fast. Genuinely fast by any scale you'd apply in daily life, but the inner core, once it starts going, collapses faster than that signal can travel. The outer core is sitting there, structurally dependent on something that no longer exists, and it hasn't found out yet. It's a bit like, and this is the only comparison I'll reach for tonight, because I think it earns its place. It's a bit like the moment a bridge support fails silently underground, and the road above continues to hold its shape for a fraction of a second purely out of inertia. Not because anything is still holding it, just because the news hasn't arrived. The outer core is, for a handful of milliseconds, a structure without a foundation. What triggers the actual collapse? The moment the Chandrasekhar limit is crossed and electron degeneracy pressure becomes insufficient, takes something like 1/10 of a second to run its full course start to finish. Core to neutron star. 1/10 of a second. I've read that figure many times, and I'm still not sure I've properly absorbed it. The most energetic transformation a stellar object can undergo, short of becoming a black hole, happens faster than a blink. Not faster than thought. Thought is actually slower than a blink, electrochemically speaking, but faster than the kind of event our nervous systems were built to track. 1/10 of a second. The inner core, the innermost region, roughly 0.6 to 0.8 solar masses of material, also collapses first. This part is almost subsonic in the sense that it collapses as a unit, coherently the whole region falling inward together faster than information can move through it, which is strange to sit with. The collapse is outrunning its own communication. Different parts of the inner core are falling without coordinating with each other, because coordination requires signals, and signals take time, and there is no time. And the outer core, everything beyond that inner region, maybe another 0.6 solar masses of iron and intermediate elements, it collapses too, but differently, supersonically, The outer core doesn't fall coherently, it falls fast and hard and without coordination, material streaming inward at velocities that reach, depending on the layer, somewhere between 1/4 and 1/3 the speed of light. Let me say that plainly, 1/3 of the speed of light, inward, material that was part of a star, iron nuclei, free electrons, a plasma that had been held in approximate equilibrium for millions of years, now moving at roughly 100,000 kilometers per second toward a central point. I keep a glass of water on my desk when I work. It's sitting there right now, doing nothing, molecules jostling at room temperature in the ordinary way. The contrast between that and what I'm trying to describe is, it doesn't even function as a contrast really. They're not on the same scale of anything. The inner core hits nuclear density and stops. This is where language starts to earn its keep or fail to. Stops is the word, but it's not a gentle stop, it's not deceleration. The inner core, which has been collapsing at a significant fraction of the speed of light, encounters the repulsive nuclear force, the short-range force that prevents nucleons from occupying the same space, and it stops on a timescale of milliseconds. The density reaches roughly 10 to the 14th power grams per cubic centimetre. A teaspoon of material at this density would weigh about as much as all of humanity combined. And the collapse hits it not like a wall exactly, because walls give a little. Walls crack and absorb. This is more like the material hits a rule, a line written into physics that says, no further, and the rule holds. The inner core overshoots slightly. It compresses past equilibrium, bounces back, not explosively, not outward in any dramatic sense, just rebounds. The compressed core pushes back against the infalling outer material with a stiffness that wasn't there a millisecond ago, and a shockwave forms. The shockwave. This is the thing that, in every popular description of a supernova, does the work. The shockwave explodes the star, the shockwave is the explosion. Except it isn't quite, and that's a conversation we'll return to. But right now, the moment of formation, the shockwave is real, and it is powerful, and it moves outward from the boundary of the inner core into the infalling outer material at speeds measured in tens of thousands of kilometers per second. It is, for a fraction of a second, the most energetic pressure front in this region of the galaxy. But here's the thing about the outer core. It's still falling inward. The shockwave is moving out, and the material of the outer core is still moving in, and these two things are meeting each other head-on inside the star, and the shockwave has to fight for every kilometre of outward progress. Every time the shockwave pushes through a new layer of infalling iron, it has to spend energy dissociating those iron nuclei, breaking them apart into protons and neutrons. Photodisintegration again, but now driven by the shockwave's heat rather than the core's radiation. And that process is expensive. Energetically expensive. Each iron nucleus disassembled cost the shockwave roughly 8 mega-electron volts per nucleon. The shockwave is paying a tax, in energy, on every layer it crosses. And the outer core has a lot of layers. There's a number I find genuinely, I want to say sobering, but it's not quite it. Clarifying maybe. The shockwave at formation carries something like 10 to the power of 51 ergs of kinetic energy, which is, that's the canonical foe, the unit sometimes used in astrophysics for supernova energetics, because 10 to the power of 51 ergs is what a typical supernova ejects, and it's a convenient benchmark. The shockwave starts with that, and as it ploughs through the outer iron core, it loses roughly 1.7 times 10 to the 51st power ergs to photodisintegration alone. More to neutrino losses as it passes through increasingly dense material. The shockwave starts with enough energy to power a supernova, and it spends more than that fighting its way out of the iron core, so it stalls. doesn't reach the surface, it doesn't explode the star, it gets somewhere between 100 and 200 kilometers from the center of the collapsing core, and it stops moving outward, and it just sits there, a pressure wave, surrounded by infalling material, losing energy faster than it's gaining it. This is the part that doesn't make it into most explanations. The shockwave stalls, the collapse has happened, the bounce has happened, the most energetic pressure wave in the local galaxy has been generated, and the star does not explode. Not yet. The shockwave sits there and the material falls through it, and the newly formed proto-neutron star at the center radiates neutrinos in torrents, and the whole system is suspended, sort of, in a state that shouldn't last, but does, for something between 100 milliseconds and a full second depending on the star. How the stalled shock eventually gets revived, and that's another chapter's problem. What I want to sit with here, at the end of this one, is just the fact of the infall itself, the speed of it, a third of the speed of light, inward, for a tenth of a second. I've been thinking about this tonight, and I keep landing on the same quiet observation. The collapse doesn't feel like a beginning, it feels like a conclusion, something that was held in place for millions of years by a series of increasingly desperate arrangements. Fusion, then helium fusion, then carbon, then the heavier stages, then electron degeneracy, then nothing finally running out of arrangements. And then the fall. Not a trigger, not a detonation, just the last support giving way, and everything that was above it finding out in sequence, at the speed of sound, that the floor is gone. The outer core falls because it must, because gravity was always there. Patient in the way that fundamental forces are patient, which is to say, not patient at all, just constant. And the only thing that was ever keeping the outer core in place was the pressure pushing back. And when the pressure went, when the electrons were captured, when the iron core reached the limit, when the inner core had already started falling, the outer core simply followed. It didn't know. It couldn't. The information hadn't arrived yet. And somewhere in those first 200 milliseconds, in a collapsing sphere of iron plasma moving at a third of light speed, the star that had been burning for millions of years stopped being a star. Not with a flash. Not outwardly. The surface was still shining, the light still travelling, the outer layers still fusing in their shells, oblivious. But at the centre, a proto-neutron star, a few tens of kilometres across, already cooling, already radiating neutrinos by the 10 to the 58 count, and above it a stalled shockwave, and above that a star that didn't yet know what had happened to its core. Somehow the shockwave eventually moves again. Somehow the star eventually explodes, or does something so close to exploding that the distinction mostly doesn't matter from the outside. How it gets the energy to do that is stranger than the collapse itself. Press your thumb against a table, hard. You feel resistance almost immediately, the table pushing back, molecules in the wood refusing to let yours pass through. That refusal isn't a decision, it's just electrons. The electrons in your thumb and the electrons in the table repelling each other. Electromagnetic force doing what electromagnetic force does, and the net effect is that solid objects don't pass through other solid objects. That's the resistance you know. That's the resistance everything in daily life runs on. What stops the collapsing core is different. Older in a sense. Deeper. Nuclear density, the density at which the collapse halts, is around 2.3 times 10 to the 17th kilograms per cubic meter. I'll let that sit there without dressing it up. What it means, practically, is that atomic nuclei are touching, not the atoms, the nuclei. The electrons are long gone at these temperatures and pressures, stripped away millions of degrees ago. What remains is nucleons, protons and neutrons, packed until there is essentially no space between them, not compressed into each other, just adjacent, fully, completely every surface touching adjacent, the interior of a large atomic nucleus scaled up to the size of a city. Now, nucleons don't want to occupy the same space. This isn't electromagnetics, it's something else. The strong nuclear force at very short distances flips from attractive to repulsive. It's what gives nuclei their size. It's why a proton has a radius at all instead of collapsing into a mathematical point. At nuclear saturation density, every nucleon is sitting right at the edge of that repulsive regime, and the force is, I want to say, enormous, but that word has been overused to meaninglessness. The force is sufficient to halt the infall of 0.6 to 0.8 solar masses of material moving at a significant fraction of the speed of light. That's a more honest measure of it than any adjective. I've been trying to think of a useful way to hold this. Not to explain it, just to hold it. The closest I've landed on is this. Imagine trying to compress a box of marbles. At first there's air between them, and they shift and rearrange. And compression is easy. Then they settle into their tightest packing and the compression gets harder. But you could still, in principle, break the marbles themselves and compress further. Now imagine the marbles can't be broken, and imagine the box is being compressed by a force that has been accelerating over millions of years of stellar gravity. That's roughly the situation. And the marbles hold. That's the thing, they hold. The inner core overshoots. I mentioned this briefly before. It's worth sitting with for a moment because it's a little strange. The infalling material doesn't just reach nuclear density and stop neatly. It overshoots. It compresses past equilibrium, past the saturation point, into a regime where the nuclear repulsion is even stronger. And then it bounces back. Not violently, or, well, actually that's not right. It is violent. Let me correct that. The rebound is extraordinarily violent by any ordinary scale. What I mean is that it's not explosive in the outward first sense we'd usually imagine. The energy of the rebound is enormous, and it becomes the shockwave we talked about last time. But the bounce itself happens in milliseconds and is contained initially within a sphere only a few tens of kilometers across. Tens of kilometers. The object that was once a stellar core the size of Earth, now, in the time it takes sound to cross a small city, compressed into something you could fit inside Cincinnati. The resulting proto-neutron star is somewhere between 20 and 50 kilometers in diameter. Hot beyond any useful comparison, hundreds of billions of degrees in the interior, spinning faster than anything of comparable mass has any right to spin, dense enough that a cubic centimetre of it would weigh roughly 1 billion tons on Earth, though the concept of weight stops making much sense at these scales. It's a new kind of object, not quite the neutron star it will eventually become. It still has protons and leptons, still has neutrinos trapped inside it that haven't had time to leave. Proto, not finished, still becoming. It's also, in this moment, the most intense source of neutrinos in the local galaxy. There's a detail about neutrino trapping that I find quietly remarkable, and I want to spend a sentence or two here because I think it reframes something. Normally, if you can use normally about neutrinos, they pass through matter without interacting. The whole chapter on them later goes into this properly. But at nuclear density, even neutrinos interact. The material is so dense that the mean free path of a neutrino drops from astronomical distances to centimeters. They can't escape. They're trapped inside the proto-neutron star, bouncing around, thermalizing, contributing to the pressure. Neutrinos, trapped. It's a little like finding out that the thing famous for passing through planets is, under the right conditions, claustrophobic. That's the only metaphor I'll use tonight, and I'm already not sure it's the right one. What I keep returning to, thinking about nuclear density, is not the numbers. Numbers at this scale become ceremonial. You recite them, you nod, you move on. What stays with me is the more basic fact that there is a flaw. Physics has a flaw. You can keep adding mass, you can keep increasing gravity, you can keep compressing, and the material will compress. Iron nuclei will disintegrate, electrons will be captured, free nucleons will pack tighter. But at some point, at this specific point, 2.3 times 10 to the 17th kilograms per cubic meter, something in the fundamental structure of matter says, here, not further. And the word isn't delivered. There's no announcement. The repulsion just becomes stronger than the compression, and the collapse, this thing that has been running at a third of the speed of light, stops within milliseconds. Outside, the shockwave is already forming. The stall is already beginning. The proto-neutron star is already cooling. Neutrinos already streaming inward, then out, in their strange, trapped, then released sequence. The physics has already moved past this moment, impatient in the way that physics is always impatient. But the flaw held. That's what I wanted to say tonight. After all the photo-disintegration, the electron capture, the infall at relativistic speeds, the disintegration of a stellar core that had held itself together for millions of years, the flaw held. A rule written into the structure of nucleons, operating at scales we've never touched and never will, did exactly what it was supposed to do. The rest of the story, the shockwave, the stall, the neutrino flood, eventually the light, all of it happens because of that. Because matter, at its most compressed, refuses. The shockwave forms at a boundary. Not a physical boundary you could point to, not a wall or a surface, but a boundary in behavior. On one side of it, the inner core, rebounding, stiffening, pushing outward. On the other side, the outer core, still falling inward, still moving at velocities the inner core was at a fraction of a second ago, still in the process of finding out that the flaw exists. The shockwave is what happens when those two things meet. Outward momentum colliding with inward momentum, and the outward, briefly, violently, and winning. For the first few milliseconds after the bounce, the shockwave is strong, genuinely strong. It carries something close to 10 to the power of 51 ergs of kinetic energy, which is, as I mentioned before, the canonical energy of a supernova. The thing that will eventually throw the outer layers of a star across several light years at thousands of kilometers per second, that energy. The shockwave has it, right now, and it is moving outward at roughly 30,000 kilometers per second. For a few milliseconds, everything looks like it's going to work, but the outer core is dense, and iron-rich, and still falling. The shockwave has to push through infalling material that hasn't stopped moving inward just because a shockwave is now moving outward through it. The two streams are interpenetrating in a region that is, by any standard, already catastrophically hot and dense. And every iron nucleus the shockwave encounters costs it around 8 mega-electron volts per nucleon to photodisintegrate, to break the iron back into the free protons and neutrons. The shockwave is doing this across an entire shell of iron continuously as it tries to move outward. The numbers are straightforward and a little brutal. The shockwave starts with roughly 10 to the power of 51 ergs. Photodisintegration of the outer iron core alone costs somewhere between 1.5 and 2 times 10 to the power of 51 ergs. The shockwave is spending more energy than it started with just crossing the iron core. It doesn't make it out. I've been sitting with that fact for a while, longer than I expected to actually. The shockwave forms with exactly the energy a supernova needs, the number we use to define supernova energetics, and it spends more than that amount fighting through 100 kilometers of iron. Not because anything went wrong, not because of some unlikely combination of factors, just because the iron core is there and it takes energy to dissociate ionish, and the shockwave has to cross it. There's a word for this kind of situation, but I can't decide if it's irony or just physics being indifferent. Probably the second one. Irony implies someone set it up. The shockwave stalls at somewhere between 100 and 200 kilometers from the center, which is, in the context of a star whose radius is millions of kilometers, essentially nowhere. The shockwave hasn't even reached the edge of what used to be the iron core. It's sitting in the middle of the collapsing stellar interior, losing energy to dissociation and neutrino losses, being pushed back by infalling material, and converting from an outward-moving pressure front into what's technically called a standing accretion shock. Standing. The word does a lot of work there. It means stationary. It means the shock is no longer advancing. It means the thing that was supposed to explode the star has, within roughly 100 milliseconds of the bounce, stopped. My desk lamp has a loose connection somewhere in the base. It flickers occasionally for no apparent reason, usually when I've forgotten about it. It flickered just now, actually, which is not relevant, but it's the kind of small thing that pulls you back into a room when your mind has been somewhere else entirely, somewhere 100 milliseconds into a stellar collapse. The standing accretion shock is a strange object. It's not doing nothing. It's still a pressure boundary, still heating and falling material as it passes through, still radiating, but it's not advancing. It's sitting there, maintained by the continuous infall of material from above and the continuous neutrino pressure from below, in a kind of equilibrium that isn't really equilibrium, because equilibrium suggests stability, and this is not stable. The proto-neutron star below it is cooling, shedding neutrinos at a rate that for the first second or so after collapse makes it briefly the most luminous object in the observable universe. Not in light, in neutrinos. Those neutrinos carry energy. Some of that energy is deposited in the region behind the stalled shock. Some of it heats the material there, adds pressure, pushes outward. Just not enough. Not yet. Here is something I find genuinely strange about that part of the story. The collapse happened in 100 milliseconds. The bounce happened in milliseconds. The shockwave formed, travelled and stalled within the first few 100 milliseconds, and now the stall, so this suspended, stationary almost failure, can last up to a full second, sometimes longer. The fastest part made the slowest problem. A thing that moved at a third of the speed of light has produced an outcome that sits nearly motionless for a second or more, waiting for something to revive it. What revives it, or what we think revives it? Because I want to be careful here, because the honest answer is that this is still one of the harder open problems in astrophysics, is neutrinos, mostly. The neutrino heating mechanism, proposed in the 1960s by Colgate and White, and refined over the following 6 decades of increasingly detailed simulation, describes how a small fraction of the neutrino luminosity from the proto-neutron star gets absorbed in the gain region, the shell of material just behind the stalled shock, and adds enough energy to push the shock outward again. Small fraction, that matters. The total neutrino energy radiated by the proto-neutron star in the first few seconds is around 3 times 10 to the power of 53 ergs. The supernova needs roughly 10 to the power of 51 ergs of kinetic energy in the ejector, so the revival requires capturing about 1% of the available neutrino energy. 1% of a very large number is still a large number, but the point is, the mechanism is not efficient. It is not elegant. It is a marginal process, sensitive to the conditions in the gain region, sensitive to turbulence and convection, sensitive to the structure of the progenitor star in ways we are still working out. And in some stars it fails. The shock doesn't revive, the star doesn't explode, it just collapses further, all the way to a black hole, and the sky doesn't brighten. The bounce then, what is it? It's the moment the collapse reverses, locally, briefly at the centre. It's the moment the nuclear floor holds and the rebound sends a shockwave outward. It's the closest thing this story has to a turning point, and it still isn't enough, on its own, to produce a supernova. It produces the mechanism, it produces the shockwave, but the shockwave has to survive the iron core, and it doesn't quite. It stalls, and then something else has to save it. The bounce is real. It's dramatic in the only way physics can be dramatic, which is by being exactly what the equations say it should be, at the scales the equations say it should happen, without any regard for whether that's satisfying. It is not the explosion, it is the thing that makes the explosion possible, under the right conditions, given the right help. Whether those conditions are met, that depends on what happens in the next second in a sphere 200 kilometers across, deep inside a star that is still, from the outside, shining normally. There's a particular quality to things that are almost happening. A kettle 2 minutes from boiling. A conversation where someone is about to say something difficult and hasn't yet. A building in the last months before demolition, still standing, still structurally present, but with something in its posture that reads as already gone. I'm not sure what produces that quality, whether it's in the object or in the observer. But the stalled shockwave has it, and I've been thinking about that tonight. The shockwave is not doing nothing. That's important to say at the outset. A standing accretion shock is a real, active, energetically sustained physical structure. It is not a pause in the story. It is the story for somewhere between 100 milliseconds and several seconds, depending on the star, depending on conditions we are still arguing about in simulations. It is a boundary and roughly spherical, sitting at around 100 to 200 kilometers from the center, where infalling material from the outer core slams into something that stops it and heats it and radiates it away as neutrinos. Standing, not stopped. There's a difference, and it matters. Picture the geometry, if you can. At the center, the proto-neutron star. Dense, hot, spinning, radiating neutrinos in quantities that dwarf anything else in the local galaxy. Surrounding it, out to maybe 50 or 70 kilometers, a region called the cooling layer, where neutrinos are being produced so rapidly that they're actually carrying energy away faster than it can be replenished. The material here is losing energy, contracting slightly, settling onto the proto-neutron star surface in a slow, continuous accretion, then from roughly 70 or 80 kilometers outward to the shock at the 100 to 200 kilometers, the gain region. This is where the balance tips the other way. Here, neutrinos streaming outward from the proto-neutron star are absorbed by free protons and neutrons. They deposit energy, they heat the material, they push outward. The gain region is, and this is the thing that every discussion of the neutrino mechanism centers on, the place where the shock could be revived. If enough energy gets deposited, if the conditions are right, and above the shock, infalling material still coming down. Always coming down, because the outer core and the stellar envelope above it haven't stopped falling just because there's a shock in the way. The shock heats the infalling material as it passes through, but it can't stop it indefinitely. The material slows, heats, radiates, and continues falling inward, adding to the accretion onto the proto-neutron star. The whole system is churning actively, none of it is still. What makes it stall, what makes the shock fail to advance despite all that activity, is a competition between timescales. There's the advection timescale, how long it takes in falling material to cross the gain region and fall through the shock onto the proto-neutron star. And there's the heating timescale, how long it takes the neutrino heating in the gain region to add enough energy to that material to reverse its motion. For a revival, the heating has to win, the material has to absorb enough energy fast enough that it starts moving outward instead of inward. During the stall, it doesn't. The material falls through the gain region faster than the neutrinos can heat it, not by a large margin sometimes. The ratio of these two timescales, often called the critical condition for explosion, can be surprisingly close to one during the stall, which is its own kind of tension. Not dramatic tension, just physical proximity to a threshold. I should say something honest here, which is that the simulations don't fully agree on what happens during this phase. One-dimensional models, where the collapse is assumed to be spherically symmetric, everything neat and orderly, almost never produce successful explosions. The neutrino heating isn't sufficient in 1D. The shock stalls and stays stalled, which initially suggested that either the neutrino mechanism was wrong or something crucial was missing from the models. What was missing, it turned out, was dimension, literally. In 2 and 3 dimensions, so the stalled shock is not steel. It develops instabilities. Convection kicks in. Hot, neutrino-heated material in the gain region is buoyant, and it rises, and cooler material sinks. And this overturning motion increases the time that any given parcel of material spends in the gain region, which increases how much energy it absorbs. The heating timescale gets shorter. The advection timescale gets longer. The ratio shifts toward explosion. There's also an instability called SASI, the standing accretion shock instability, which causes the shock to oscillate and slosh, developing large-scale asymmetric motions that further amplify the neutrino heating and push material outward in particular directions. The stall in 3 dimensions is alive with motion. It just hasn't found the right direction yet. Something I read once, I can't place where now, some review paper late at night with bad coffee going cold beside the keyboard, described the stalled shock as a system on the verge of explosion for extended periods, which struck me as one of the more quietly unnerving descriptions I'd encountered. Not exploding, not failing to explode, on the verge, for hundreds of milliseconds, for up to a second, held at the edge of something. The neutrino luminosity from the proto-neutron star peaks in the first second. This is when the most neutrinos are being produced, when the proto-neutron star is hottest, when the flux through the gain region is highest. If the shock is going to be revived by neutrino heating, it's most likely to happen during this window. After a few seconds, the neutrino luminosity drops, the proto-neutron star cools, the neutrino production rate decreases, and the chance of revival decreases with it. Some shocks revive at 200 milliseconds, some at 500, some in simulations push toward a full second before finally advancing, and some don't advance. The star collapses completely, quietly, no optical brightening, no ejected envelope, just a very massive star that was there and then, a few seconds later, isn't, replaced by a black hole and a fading neutrino signal that no one was probably watching for. There's a number that I find, and I want to be precise about this word, clarifying rather than dramatic. The critical neutrino luminosity for explosion. The minimum neutrino output from the proto-neutron star needed to revive the stalled shock. It's not a fixed number. It depends on the mass of the collapsing core, the accretion rate, the progenitor structure. But for typical conditions, it's somewhere in the range of a few times 10 to the power of 52 ergs per second for a few hundred milliseconds. The sun's total luminosity, light, heat, everything, is 3.8 times 10 to the 26th power watts. The proto-neutron star in neutrinos alone during the stall is radiating at roughly 10 to the 45th power watts, not comparable, not on the same scale. The comparison doesn't illuminate anything, I almost didn't make it, because the numbers are so far apart that the mind just produces a kind of white static instead of understanding. Let it be large, that's enough. The thing about the stall, the thing I keep coming back to, is that it reframes what a supernova is. If the shock had just travelled outward continuously from the bounce, if the nuclear flaw had pushed it out and kept it moving, you could still argue that the explosion came from the collapse, but you could at least point to a moment of origin. A bounce, a shockwave, a star disrupted, cleanish, explicable in the paragraph. But the shock stalls, and the revival comes from something that had nothing to do with the bounce. It comes from neutrino heating of a thin shell of material in a region between 70 and 200 kilometers from the center, over the course of hundreds of milliseconds of convective churning and shock oscillation. The bounce isn't sufficient. The collapse isn't sufficient. What eventually produces the supernova is this marginally heated, turbulently convecting, asymmetrically sloshing shell of matter, inching the shock back outward a few kilometers at a time, until the balance tips and the shock doesn't stall again. It's not an explosion in any sense that the word implies. It's a threshold, crossed after deliberation. The stall will end. In the stars that become supernovae, it always ends. Something in the gain region tips the balance. More heating, deeper convection, a lucky oscillation mode from SASI that sends material outward in a concentrated burst. The shock starts moving, slowly at first, then faster as it reaches less dense material and has less to push through. It will take hours to reach the surface of the star. But right now, in this chapter, in this geometry, the proto-neutron star cooling at the center, the gain region churning, the standing shock oscillating at 100 to 200 kilometers, the star is suspended, not exploding, not collapsing further, just between states, held at the edge of what it's about to become, almost happening, the way things are right before they do. Start with the energy, not to dramatize it, just to establish it, the way you'd establish the dimensions of a room before describing what's in it. The gravitational binding energy released when a stellar core collapses to a neutron star is approximately 3 times 10 to the 53rd power ergs. That number will mean different things to different people depending on how much time they've spent with large numbers, so let me offer one frame and then step back from it. This is roughly the total energy output of the Sun over its entire 10 billion year lifetime times 100, released in a few seconds, from an object that used to be the size of Earth and is now the size of a city. That's the room we're in. Now, how much of it do we see? The supernova, the optical event, the brightening, the thing that outshines galaxies and appears in historical records and gets spotted by amateur astronomers in spiral arms of distant galaxies, uses about 1% of that energy, sometimes less. The kinetic energy of the ejected envelope, which is the actual physical explosion if we're going to use that word, is typically around 10 to the power of 51 ergs. The light we see is a fraction of that. Most of the optical luminosity comes from radioactive decay of nickel-56 produced in the explosion. The shockwave's direct light contribution is actually relatively brief. 1%. The other 99% leaves the star as neutrinos, not gradually, not over days, the way a cooling object radiates heat. In the first 10 seconds after the core bounce, the proto-neutron star emits something like 10 to the power of 58 neutrinos, roughly the same order of magnitude as the number of atoms in the Earth, in particles, in 10 seconds, carrying away the bulk of the gravitational binding energy in a burst that, if you had a detector sensitive enough, you could watch from the other side of the galaxy. The burst lasts maybe 10 to 15 seconds for the bulk emission. After that it tapers, the proto-neutron star cooling over minutes and hours, emitting neutrinos at decreasing rates as it settles. 10 seconds for 99% of the energy of the most energetic stellar event in the known universe. The reason is thermodynamics, essentially. The core collapse produces an object of extraordinary temperature, hundreds of billions of degrees, and at those temperatures, the dominant cooling mechanism isn't radiation in the electromagnetic sense. It's neutrino production. Thermal neutrinos, produced in particle-antiparticle pairs across all three flavors, stream outward from the cooling proto-neutron star in quantities and at luminosities that make electromagnetic radiation look like a footnote. The core is, in the language of astrophysics, neutrino-dominated, not partially neutrino-cooled, not primarily dominated. The entire energy budget of the collapse flows through this channel, and the channel is invisible to every optical telescope ever built. There's a quality to this fact that I find, and I've been trying to find the right word for a while. I want to say it's humbling, but that's reached for too quickly. Something more like disorienting, because we've been watching supernovae for as long as we've been watching the sky. Historical records of stellar brightening go back thousands of years. The 1054 supernova that left the Crab Nebula was documented by Chinese astronomers. Tycho Brahe built a large part of his reputation on SN 1572. Kepler watched one in 1604. These events were among the most carefully observed phenomena in pre-modern astronomy, and every single observation captured the 1%. The 99% passed through every astronomer who ever looked up, through the stone walls of observatories, through the planet, gone before the light had even fully brightened. I've got a window across from where I usually sit, and tonight there's nothing to see through it. Heavy overcast, no stars, just the faint orange ambient glow of the city reflecting off low cloud. Which is, in its own way, a small version of the same problem. What's actually happening above those clouds is invisible from here. The light that reaches me is the residue, not the event. Neutrinos, though, the ones from a supernova in this galaxy, which will happen eventually, statistically, probably within the next few centuries, would pass through that cloud, through the glass, through the building, through me, through the planet, and out the other side slightly attenuated, barely affected. You cannot build a cloud for neutrinos. There is no material that stops them at any scale a human civilization could arrange, almost no material. This is where the story gets strange in a way that took decades to fully work out. At nuclear density, inside the proto-neutron star itself, neutrinos are trapped. The mean free path, normally measured in light years, drops to centimeters. The material is so dense that even neutrinos interact. They thermalize. They become part of the energy content of the proto-neutron star interior, diffusing outward slowly over seconds, rather than streaming out instantly. This trapping is actually critical. If neutrinos escaped freely the moment they were produced, the collapse would proceed differently. The core would cool too fast, The bounce dynamics would change. The shockwave might not form the way it does. The trapping and the subsequent diffusion are the neutrinos working their way outward through increasingly less dense material until they reach the neutrinosphere. The surface of the last scattering. This is part of the machinery. The delay is functional, and then they leave. All at once, roughly, in that 10-second burst. What fraction of them get reabsorbed on the way out? About 1%. Of the 99%, 1% gets captured in the gain region and helps revive the stalled shock. The rest continue outward, through the stellar envelope, through the shock itself, out into space at the speed of light, or very nearly given their small but non-zero mass. And they do not stop. They don't know there was a star in the way. I almost wrote, they don't care, and then pulled back from it, because caring isn't something neutrinos do. And assigning them indifference implies they had the option. They don't interact. That's all. It's not indifference, it's just physics. The weak force is weak. Interactions require proximity and the right conditions, and most neutrinos in most material never find them. So this is the accounting. A collapse releases 3 times 10 to the 53rd power ergs. Roughly 3 times 10 to the 52nd power of that gets deposited in the gain region by neutrino heating, of which perhaps 10 to the power of 51 ends up as kinetic energy in the explosion. The light we see is a fraction of that. The neutrino burst carries the rest on almost everything out into the universe, where it joins a diffuse background of supernova neutrinos accumulated over the entire history of cosmic star formation. That background exists, right now, a faint, cold, nearly undetectable sea of neutrinos, each one carrying a small piece of energy from a star that collapsed somewhere, at some point in the last 13 billion years. Passing through everything, accumulating. We exist inside it and have no way to feel it. The 1% is what we built our understanding of supernovae on. The light curves, the spectral lines, the expanding nebulae, the element abundances. Everything we know about these events observationally, almost all of it, comes from the residue. The shockwave heating the envelope, the nickel decaying to cobalt to iron and lighting the ejector from inside, the optical brightening that peaks over days and weeks. The 99% was inferred, theorized, and then, once, measured. In 1987, a star in the Large Magellanic Cloud collapsed, and 25 neutrinos were detected across 3 underground observatories in a 13-second window, hours before the optical brightening arrived. 25 particles, from 10 to the power of 58. But the timing was right, the energies were right, and for the first time the 99% left a mark small enough to count. I keep returning to the proportion, 99%. Not because it's surprising exactly. The physics is clear enough once you understand the temperatures involved and the dominance of neutrino cooling. It is more that it reframes the whole vocabulary we use for these events. We call them the brightest explosions in the universe. We say they outshine galaxies. Both things are true in the electromagnetic sense. But in total energy terms, the light is an afterthought. A byproduct of a byproduct. The shockwave is driven by 1% of the neutrino energy absorbed in the gain region, which is itself 1% of the total neutrino emission, which is itself 99% of the collapse energy. The thing we see is very far downstream from the thing that happened. Whether that makes supernovae less remarkable or more, I'm genuinely not so sure. Maybe the question doesn't hold up. The light still crosses galaxies. The elements still get made. The shockwave still disrupts a star. It's just that most of the event was always invisible. We were always only seeing the edge of it. Right now, while you're reading this, neutrinos are passing through you. Not metaphorically, not in some loose sense of cosmic connectivity that gets pulled out for effect, physically, literally. Something like 65 billion solar neutrinos produced in the fusion reactions at the Sun's core, travelling the 150 million kilometres to Earth in about 8 minutes, pass through every square centimetre of your body every second, through the hand holding the phone or resting on the pillow, through the blanket, through the mattress, through the floor and the foundation and the rock below it, through the planet itself and out the other side, barely attenuated. You've never felt one. You will never feel one. This is not because neutrinos are small. It's because they barely interact with matter through the weak nuclear force. And the weak force, despite being one of the 4 fundamental forces of the universe, is extraordinarily reluctant to do anything. The weak force operates at ranges smaller than an atomic nucleus. Its carrier particles, the W and Z bosons, are heavy, which in quantum field theory terms means the force they mediate drops off fast and or hard. For a neutrino to interact with a proton or neutron, it has to pass within roughly 10 to the power of minus 18 meters. For context, the proton itself is about 10 to the minus 15 meters across. The interaction range is 1,000th of the size of the thing being hit. This isn't a loose impressionistic way of saying neutrinos are unlikely to interact. It's the actual geometry of the problem. The cross-section, effective target area, for a typical neutrino hitting a nucleus is around 10 to the power of minus 44 square centimeters. If you wanted a material dense enough to stop half the neutrinos passing through it, you'd need a light year of lead. A light year of lead. I wrote that and then sat back for a second, because it doesn't feel like a real sentence. But it is. That's the actual number. So here is the thing that needs to hold 2 ideas at once, because the supernova story requires both of them to be true simultaneously. Neutrinos almost never interact with matter, a light year of lead, the planet beneath you, the entire stellar envelope of a dying star, all essentially transparent. And yet neutrinos are the primary mechanism by which core collapse supernovae explode. Both of these are true. The resolution is in the numbers, not the physics. The interaction probability per neutrino is absurdly small, but the number of neutrinos produced in the first seconds of a core collapse is around 10 to the power of 58, and the material they are passing through in the gain region just behind the stalled shock is not lead. It's a plasma of free protons and neutrons at densities and temperatures where the weak force cross-section increases, and the distance the neutrinos have to travel through that material is only a few tens of kilometers. Tiny probability, enormous number, short distance, dense target. The math works out to roughly 1% absorption in the gain region, which, as we said before, is enough. There's a radiator in the hallway outside this room that makes a ticking sound as it cools down at night. Metal contracting, the same sound every winter. Irregular enough that I still notice it sometimes. It went off a few minutes ago, 3 ticks in quick succession, and I found myself thinking about detection, about what it means for something to leave a mark. The radiator leaves a mark. Expansion and contraction, thermal stress, eventual wear, for a cycle does something. The neutrinos passing through the building right now, through the radiator itself, do essentially nothing. They are not accumulating stress. They are not wearing anything down. They are passing through the metal's atomic structure the way a thought passes through a room, present, in some physical sense, and leaving nothing behind. Except when they don't. In 1987, the supernova in the Large Magellanic Cloud, SN 1987A, produced a neutrino burst that reached Earth roughly 3 hours before the optical brightening. 3 underground detectors caught it. Kamiokanda 2 in Japan detected 12 events. IMB in Ohio, actually Ohio, which I find quietly satisfying for no defensible reason, detected 8. Baksan in Russia detected 5, 25 neutrinos total across 3 detectors in a 13-second window, from a burst of 10 to the power of 58. The detectors were large tanks of ultra-pure water, surrounded by photomultiplier tubes, watching for the faint flash of Cherenkov radiation produced when a neutrino, very rarely against all probability, collided with a water molecule and produced a charged particle moving faster than light travels through water. Not faster than light travels in vacuum, faster than light travels through water. The particle creates a kind of optical shockwave, a blue flash, and the photomultipliers catch it. 25 flashes in 13 seconds from a star 160,000 light-years away. It was enough. The energies matched the theory, the timing matched the theory. The neutrino mechanism, which had been theoretical since the 1960s, had left a mark. What the neutrinos do inside the star on their way out is worth following in some detail, because it's easy to think of it as simple passage, and it isn't. They're produced throughout the interior of the proto-neutron star, thermal pairs of every flavour. Electron neutrinos from electron capture, the full spectrum. Deep in the interior, where densities exceed nuclear saturation, they're trapped, scattering off nucleons repeatedly, diffusing outward in a slow random walk rather than streaming freely. As they diffuse outward and the density decreases, they reach a region called the neutrinosphere, a loose flavor-dependent surface where the material becomes thin enough that further scattering is unlikely. From here they stream outward more freely, but more freely is relative. They still pass through the gain region, the shell between roughly 70 and 200 kilometers, and in there some of them are absorbed. A neutrino hits a neutron and produces a proton and an electron, or an antineutrino hits a proton and produces a neutron and a positron. These reactions deposit energy. They heat the gain region. They push the stalled shock, 1% of them. The rest continue outward through the stalled shock, through the infalling outer core, through the stellar envelope, millions of kilometers of plasma, and out into space carrying 99% of the collapse energy with them, as if the star were barely there. There's a question I keep approaching and not quite asking, which is whether passing through is the right frame for what neutrinos do. Because passing through implies traversal, entering one side, exiting the other, the object unchanged. But the neutrino that passes through you is not the same neutrino that entered. Not exactly. Neutrinos oscillate between flavors as they travel. Electron, muon, tau, a quantum mechanical process that requires them to have mass, which they do, though we don't know the exact values. The neutrino that exits the other side of the planet may be a different flavor than the one that entered. Something changed, something propagated and transformed and continued. Whether that counts as passing through or something else, I'm not sure the language has a clean answer. Physics does, the math describes it precisely, but the intuitive word for it hasn't quite been found yet, or maybe it doesn't need one. The 10 to the power of 58 neutrinos from a core collapse supernova don't all go the same direction. They radiate outward in all directions, spherically, roughly, and as they spread, flux decreases with the square of the distance. By the time they reach a detector on Earth, even from a supernova in the same galaxy, the flux is small enough that catching 25 of them requires a detector the size of a swimming pool filled with ultra-pure water, watched by hundreds of photomultiplier tubes, running continuously, buried underground to shield it from cosmic ray backgrounds, and still 25 from 10 to the power of 58. The fraction that interacts is so small it's almost a rounding error. And yet those 25 interactions confirmed a mechanism that physicists had spent 30 years building the theory for, confirmed the temperature of the proto-neutron star, the duration of the neutrino burst, the total energy released. 25 marks left in water, by particles that pass through lead for a light year without stopping. What I find myself turning over at this hour thinking about neutrinos in the context of the supernova story is something like this. The thing that makes them useful as a cooling mechanism, their reluctance to interact, their ability to carry energy out of the collapsing core faster than photons ever could, is the same thing that makes them almost impossible to detect and almost invisible in their effects. The property that makes them the dominant energy channel and the most energetic stellar event in the universe is the same property that lets them pass through your hand right now and leave no trace. The weakness is the mechanism. The invisibility is the point. I'm not sure that's a satisfying thought. It might be the kind of thing that sounds profound at a certain time of night and falls apart in daylight. But it keeps returning, so I'll leave it here. Slightly open, not quite concluded. Because some things are worth holding without resolving. 99% of everything gone through matter as though matter were a suggestion. And 1% somehow, enough to light a star from the inside out. There is no single moment. That's the first thing to say, and it's worth saying plainly before anything else, because the story of the shock revival has a natural pull toward drama, toward a threshold crossed, a switch thrown, a clear before and after. The physics doesn't provide that. What it provides instead is a gradual shift in a competition that had been running for hundreds of milliseconds, a balance that tips slowly, unevenly, in different directions at different times, until the shock is moving outward more than it's being pushed back, and the question of whether it will explode changes from uncertain to settled. Not a moment. A process that, looked at from outside, eventually looks like a moment. The stalled shock has been sitting at roughly 100 to 200 kilometers from the center for something between a few hundred milliseconds and close to a second. During that time, it hasn't been static. We talked about this. It's been oscillating, developing asymmetries, the gain region behind it churning with convection as hot neutrino-heated material rises and cooler material sinks, and the whole structure sloshes in modes driven by the standing accretion shock instability. It looks, in three-dimensional simulations, almost turbulent. Not smooth, not spherical, more like a bubble being pushed at from multiple directions simultaneously, deforming, recovering, deforming again. The turbulence is doing something useful. Here's the mechanism, stated as plainly as I can manage it. Material falling through the shock enters the gain region. If it moves through the gain region quickly, advected inward faster than neutrinos can heat it, it falls onto the proto-neutron star without contributing to the revival. The advection timescale wins over the heating timescale. And the shock gets no help. But turbulence slows the material down, not dramatically, not by orders of magnitude, but meaningfully. Convective overturning in the gain region, the rising and sinking of parcels of material at different temperatures, increases the dwell time. A parcel of matter that might have taken 50 milliseconds to cross the gain region in a smooth laminar flow might take 80 or 100 milliseconds in a turbulent one. That extra time means more neutrino absorption, more energy deposited, more pressure pushing outward. The ratio of heating timescale to advection timescale, the number that determines whether explosion occurs, shifts slowly, unevenly. Some regions of the gain region tip into net outward motion before others. The shock begins to expand in those directions first, becoming spherical, a lumpy and irregular surface rather than a clean sphere. This is not the supernova as it looks in any illustration you've ever seen. It's messier, more contingent. SACI contributes differently. The sloshing motions of the shock, large-scale oscillations that can grow to amplitudes of tens of kilometers, redistribute energy in the post-shock region in ways that complement the convective heating. There are conditions in some simulations where SASI appears to be the dominant effect driving revival. In others, convection dominates. In most realistic three-dimensional models, both are operating simultaneously, interacting, sometimes reinforcing, sometimes competing, and isolating the contribution of each is genuinely difficult. The simulations don't always agree on the relative importance. I find this worth saying because it's easy to give a clean account of the revival mechanism, and it is not fully clean. The broad strokes are well established. Neutrino heating, turbulence amplifying the efficiency of that heating, the shock eventually reviving. The fine details. Which instability mattered most in which progenitor, exactly when and where the shock first began to advance, how much the symmetry in the revival affects the eventual explosion energy. These are active research questions. The most realistic simulations are running now on machines that would have been implausible a decade ago, and they are producing explosions, which is progress. But they're not yet producing the full range of observed supernova energies reliably. We know the mechanism, we don't fully know the machine. My neighbour's dog started barking at something about 20 minutes ago, and then stopped just as abruptly, the way dogs do, absolute certainty about a threat, then complete indifference. I mention it only because the contrast is striking here. A quiet house, unremarkable night, a dog having a momentary crisis and moving on. A stellar interior where a shockwave has been grinding against infalling material for nearly a second and is, by degrees, starting to win. The shock, when it begins to advance again, does so at speeds much lower than its initial post-bounce velocity. It has spent most of its kinetic energy. It's being driven now primarily by neutrino energy deposited in the gain region, which is continuously being replenished as the proto-neutron star continues to radiate. It moves outward at perhaps a few thousand kilometers per second in the early revival phase. Fast, but nothing like the tens of thousands of kilometers per second it had at formation. It's slower, but it's moving, and the material it's now entering is less dense than the iron core it originally stalled in. This is where the geometry changes in the star's favour for a change. The iron core, the dense, energy-hungry material that cost the shockwave so much, it is behind the shock now. It was dissociated, accreted, processed. What's ahead of the revive shock is the silicon and oxygen and neon shells of the star, progressively less dense as the shock moves outward through layers that were never compressed to iron core densities. The photo-disintegration tax drops. The shockwave begins to accelerate, not immediately, not in a clean ramp. The density profile of the progenitor star is not smooth. There are composition interfaces, shell boundaries, places where the density drops sharply, and each time the shockwave crosses one of these boundaries it accelerates as the resistance decreases. The shock's progress outward is a series of accelerations rather than a constant velocity. It will take hours to reach the surface of the star. Hours. After everything that preceded it happened in milliseconds and seconds, the core collapse, roughly 100 milliseconds, the bounce milliseconds, the stall up to a second, the revival, beginning within that first second, the shock advancing over the following minutes. But the stellar envelope is large, The star might have a radius of hundreds of solar radii. Some red supergiants extend to nearly 1,000, and even a shock moving at 10,000 kilometers per second takes hours to cross that distance. There's something about that timescale I find clarifying, I think. The violent interior physics, the nuclear densities and relativistic infall and neutrino floods, all of that compressed into the first second, and then a long, comparatively quiet propagation through the outer star. A shockwave heating and accelerating material that had no idea what was happening to its core hours earlier. The surface of the star still shining, still emitting light from shell fusion. The photosphere completely unaware. As the shockwave propagates outward through the stellar layers, it processes the material it passes through. Temperatures behind the shock reach billions of degrees, enough to drive explosive nuclear synthesis in the oxygen and silicon shells. Elements are made, nickel-56 in abundance in the innermost ejector, where temperatures are highest, lighter elements in the outer layers. The R process, the rapid neutron capture that builds the heaviest elements, may occur in the neutrino-driven wind off the proto-neutron star, or in particular conditions near the shock, though the exact site of R-process nucleosynthesis in core collapse supernovae is still debated. The shockwave is not just moving matter, it's changing it. Iron and silicon and oxygen are being rearranged at temperatures that don't exist anywhere else in the contemporary universe except in other dying stars. The material that will eventually be ejected, that will drift through the galaxy for millions of years before being incorporated into new star-forming clouds, is being assembled right now, in a wave of nuclear processing, behind a pressure front that started as a rebound from a flaw. The revival, then, what was it? It was turbulence doing what turbulence does in a hot, unstable medium, creating mixing, redistributing energy, slowing the outward flow of material just enough to let neutrinos do more work. It was SASI growing large enough to shift the energy budget in the post-shock region. It was the proto-neutron star continuing to radiate at luminosities that, for that first second, were extraordinary, providing a continuous energy source that the stalled shock could eventually draw on. It was not a single cause. It was a convergence of conditions that, in this star at this moment, happened to tip in the direction of explosion. In another star with a slightly more massive core or different progenitor structure, it might not have. The shock might have stalled and never recovered. The star would still have collapsed. The neutrinos would still have left. But no optical brightening, no ejector, no supernova. The revival is not guaranteed. It never was. What the shock becomes after revival is something different from what it was at formation. At formation, it was a strong shock carrying the full kinetic energy of the core rebound. After stalling and being revived by neutrino heating, it's a neutrino-driven outflow, sustained by continuous energy input from below, expanding through progressively less resistant material, accelerating toward the stellar surface. It's gathering speed now, hours from the surface. The star above it unchanged, still fusing, still shining, in wavelengths that have no information about what's rising through the interior below them. The light that will eventually tell us a supernova happened hasn't been produced yet. It will require the shock to reach the surface, break out, and set the envelope moving at thousands of kilometers per second. That breakout, the shock emerging from the stellar surface for the first time, releases a brief, intense flash of X-rays and UV. Shock breakout. It lasts minutes to hours, depending on the star's radius. For most of the history of astronomy, we never caught it. Now sometimes we do, but that's the next chapter's territory. Right now the shock is still inside the star, moving through oxygen and neon and carbon shells, processing and heating, carrying the energy of a collapsed stellar core outward at thousands of kilometers per second through layers of material that have been sitting there since the star first formed. Going up. Finally, after everything, just going up. The shockwave has been travelling for hours, not minutes. Hours. The core collapsed, the bounce happened, the stall ran its course, the revival began. All of that in the first second. And then the shockwave started climbing outward through silicon and oxygen and neon and carbon and helium, through layer after layer of material that had been sitting undisturbed for thousands of years of stellar evolution. And the climbing took hours because the star is large, because even 10,000 kilometers per second is slow when the distance is measured in stellar radii. And some red supergiants have radii approaching 1 billion kilometers. The star's surface has known nothing of this. Photons from the stellar photosphere, the light we would have been seeing from this star for the entire duration of its life, are still being produced by the shell fusion far above the collapsing core, still diffusing outward through the stellar atmosphere, still leaving the star at the speed of light in every direction. The spectrum is unremarkable. The luminosity is normal. Whatever telescopes might have been pointed at this star in the hours before the shock arrived at the surface would have recorded nothing unusual. An ordinary star shining ordinarily, while something catastrophic rose through its interior. At some point, the exact timing depending on the stellar radius, the shock velocity, the density profile of the outer layers, the shockwave reaches the base of the stellar envelope. The material here is less dense than anything the shock has encountered since the early moments of its propagation. The resistance drops sharply, the shock accelerates, and the enormous thermal energy deposited behind the shock, the heat of compression, the radiation from billions of degree plasma, starts to have a surface to reach. This is shock breakout, and it is brief. The duration of the breakout flash depends on how long it takes the shock to cross the stellar atmosphere. Typically light travel time across the stellar radius, which for a compact blue supergiant might be seconds, and for an extended red supergiant might be an hour or more. The emission is primarily X-rays and ultraviolet. Not visible light. Not yet. The temperatures at breakout are too high for optical EO. The peak of the radiation is far into the UV, sometimes into soft X-rays. We didn't detect shock breakout directly in real time until 2016, a star in a galaxy 1.2 billion light-years away, caught by the Kepler Space Telescope, which happened to be watching that part of the sky when the breakout flash occurred. Kepler was designed to find exoplanets. It found this accidentally, in data that someone was patient enough to look through. The window above my desk has been dark for hours, the kind of dark that feels different at 3 in the morning than it does at 10 at night, heavier somehow, more committed to being dark. I mention it because there's something about the hours between shock revival and shock breakout that feels like that kind of dark. Not empty, just unrevealing. Everything happening out of sight, beneath a surface that shows nothing. And then, when the shock breaks through, the flash. Brief, hot, high energy. Gone in minutes or hours. The first light the event has produced that carries any direct information about the explosion itself. Most supernovae, we miss this entirely. After breakout, the envelope, the outer layers of the star, now being accelerated by the shock to velocities between 5,000 and 30,000 kilometers per second depending on layer and depth, starts expanding. It's moving outward. What was the star's atmosphere is now ejecta, a rapidly expanding cloud of hot gas, carrying the processed elements the shockwave made on its way up. The kinetic energy in this ejecta is roughly 10 to the power of 51 ergs, the canonical supernova energy, the 1% we discussed, and it will continue expanding, cooling, thinning for years and decades and eventually millennia. But in the first hours and days, it's dense enough that photons produced inside it can't escape immediately. The ejector is optically thick. Light bounces around inside it, thermalizing, getting absorbed and re-emitted, slowly diffusing outward. The optical brightening we associate with a supernova, the thing that peaks over days to weeks and then fades over months, is not the shock breakout. It's not the shockwave hitting the surface. It's the photosphere of the expanding ejector. As the ejector expands and thins, the photosphere, the surface from which photons can finally escape, moves inward through the ejector in mass coordinate terms, revealing progressively deeper, hotter material. What we see watching a supernova brighten and peak and fade is a photosphere retreating through an expanding cloud of elements. The peak luminosity for a typical core collapse supernova comes days to weeks after the initial explosion. Not because the explosion is still ongoing, the explosion, in any meaningful physical sense, was over in the first second. The peak comes from radioactive decay. Nickel-56, synthesized in the innermost ejector during the shock's passage through the silicon shell, decays to cobalt-56 with a half-life of about 6 days. Cobalt-56 decays to iron-56 with a half-life of about 77 days. Each decay releases gamma rays, which thermalize in the ejector and are radiated as optical and infrared light. The light we see at peak is nuclear decay energy. The star's core processed into radioactive nickel by the shockwave heating the ejector from inside as it expands. The actual explosion, the collapse, the bounce, the neutrino flood happened weeks before the light we're watching was produced. This is the detail I keep returning to. This is the one that reframes everything most quietly. Supernovae, as objects of astronomical observation, are studied primarily through their light curves, how they brighten and fade, and their spectra, which elements appear in absorption and emission at what velocities at what times. These are extraordinarily information-rich observations. We've learned an enormous amount about stellar evolution, nucleosynthesis, progenitor structure, explosion energy, ejector composition. The light curves of Type 1a supernovae are calibrated precisely enough to measure cosmological distances, which is how dark energy was discovered. All of this, all of it, comes from the afterglow, the radioactive decay, the expanding photosphere, the shock-heated envelope cooling into visibility over days and weeks. None of it comes from the collapse itself. None of it comes from the bounce, the stalled shock, the neutrino revival. We cannot see those events with optical telescopes. We infer them from models, from the properties of the light that arrives weeks later. The light is a consequence of a consequence of a consequence of the thing that happened. There's a metaphor I've been resisting using because I think it's almost right but not quite. The idea that watching a supernova is like hearing thunder, the event already passed by the time the signal reaches you. It's almost right. The delay is real. The information is genuine but late. But thunder tells you something direct about the lightning. It's the same event, just slow. The optical light from a supernova is a few steps removed. It's not the explosion directly. It's radioactive material the explosion produced. Decaying, heating gas, which then radiates. It's more like hearing a sound made by an instrument built by a process set in motion by the storm. Actually, that's too complicated. Let me leave it as the light is late, and it's not direct, and it's still real. The first photons that carry any information about the supernova, the shock breakout flash, travel at the speed of light across whatever distance separates the star from Earth. For a supernova in the Milky Way, that's somewhere between a few hundred and tens of thousands of light years, depending on where in the galaxy it occurs. The photons arrive, they enter telescopes, or if the event is bright enough, and they produce an impression. And the news they carry is already hours old when they left the star, because it took the shockwave hours to reach the surface after the core collapsed. For SN 1987A, 160,000 light-years away, the neutrinos arrived at Earth roughly 3 hours before the optical brightening. Not because neutrinos are faster than light, because neutrinos left the star at the moment of core collapse, and the light left the star hours later when the shock finally broke through the surface. The neutrinos were carrying older news, more direct news. The light was younger and knew less. I find it genuinely hard to overstate how much of what we know about supernovae is built on the downstream signal. It's not a criticism. The light is rich with information, and astronomers have extracted from it things that would have seemed miraculous to earlier generations. The composition of the ejector, the velocity structure, the mass of the progenitor sometimes, by matching the light curve to models, the explosion energy, but the explosion itself, the thing this whole series of chapters has been describing, happens in darkness, in the interior of a star, in a second, and what emerges hours and days and weeks later is light from the debris. The star is already gone when we see it brighten. The core is already a neutron star or a black hole, already cooling, already settling into whatever it's going to be for the next billion years. The shockwave has already done its work, the nickel is already decaying, and we're watching the glow of that from very far away and calling it an explosion, which it is, mostly, just not the way the word usually implies. Start with something small. In 2009, a star in NGC 6946, a galaxy about 22 million light-years away, spiral-armed, unremarkable in most respects, except that it has produced 10 observed supernovae in the last century, which is why astronomers call it the fireworks galaxy. A star in that galaxy brightened slightly, not dramatically, a modest increase in luminosity, the kind of thing that gets flagged and watched but doesn't make headlines. Astronomers pointed telescopes at it. They noted it. They waited for what usually comes next. What usually comes next is the supernova, the rapid brightening over days, the peak, the spectral lines. None of that came. The star faded. Over the following months it became dimmer than it had been before the brightening. By 2015, when the Hubble Space Telescope was pointed at the location, the star, a red supergiant estimated at around 25 solar masses, the kind of star that by all reasonable expectation should have ended in a core collapse supernova, was gone. Not obscured, not variable, gone. The designation is N6946-BH1. The leading hypothesis is that the star underwent core collapse and formed a black hole without a successful supernova explosion. The slight brightening in 2009 may have been the shock breakout, or a pre-collapse outburst, or the brief optical transient associated with mass being swallowed as the black hole formed. There are competing interpretations and none of them are settled. What seems fairly clear is that a massive star collapsed and did not produce a supernova. It just stopped being visible. I've been thinking about how to hold that. A star 25 times the mass of the Sun, burning for millions of years, fusing hydrogen, helium, carbon, all the way up to iron, reaching the Chandrasekhar limit, collapsing, and then no explosion, no ejected envelope, no expanding nebula that will drift through the galaxy for tens of thousands of years. No elements scattered into space, just a black hole and a galaxy that has one fewer bright point in it, and a brief dim transient that a few astronomers noticed because they were paying attention. It's a strange thing to sit with, not sad exactly, and stars don't have stakes in their own endings, but something adjacent to that. The sense of an enormous process running all the way to its conclusion and then not producing the outcome the conclusion was supposed to lead to. The physics of failed supernovae follows from what we've already covered, which almost makes it worse. The stalled shock needs neutrino heating to revive. The neutrino heating has to exceed a critical luminosity. The gain region has to absorb energy faster than the advection timescale removes it. And this condition is not always met. It depends on the mass of the collapsing core. It depends on the accretion rate onto the proto-neutron star. It depends on the progenitor's structure in ways that are still being mapped. Roughly speaking, more massive cores are harder to explode. The accretion rate onto the proto-neutron star is higher for more massive progenitors, which means more material is falling through the gain region quickly, which means the advection timescale is shorter, which means neutrino heating has less time to do its work. The critical neutrino luminosity required for revival is higher, and the proto-neutron star, which is also more massive, may not be hot enough or compact enough. Provide it. There are also cases where the proto-neutron star itself exceeds the maximum neutron star mass during the accretion phase and collapses to a black hole before the shock revives. The neutrino signal cuts off. The accretion continues. The shock, if it was close to reviving, loses its energy source and falls back. The window closes quietly. Something just occurred to me that I keep not quite saying directly, so let me say it. Failed supernovae are expected. They're not anomalies, not failures of our models. The same physics that produces successful explosions in some mass ranges predicts failed ones in others, particularly for progenitors above roughly 20 to 25 solar masses, though the boundary is not sharp and depends on factors like rotation and magnetic fields and the detailed structure of the progenitor. Current estimates suggest somewhere between 10 and 50% of all core collapses in the universe may not produce successful supernova explosions. That's a wide range, and I want to be honest about why it's wide. The models don't fully agree. The observational constraints are limited because failed supernovae are, by definition, hard to observe. You're looking for something that isn't there, which requires knowing what should have been there, which requires pre-explosion imaging of the progenitor star. We have that for a small number of cases. N6946-GH1 is the strongest candidate. There are others less certain. The radiator in the hallway has gone quiet now. Earlier it was clicking as it cooled. Now it's just done, settled. No more noise. I notice these small endings more than I probably should. Processes running to completion without announcement. What happens to the material that doesn't get ejected? Most of it falls inward. The outer layers of the star, without a shockwave to accelerate them, lose their support and begin falling toward the forming black hole. Some of the envelope may be partially ejected by the neutrino-driven wind in the brief period before black hole formation. A faint transient may be detectable in principle, not yet confirmed observationally, but the bulk of it accretes. The iron core, the silicon shell, the oxygen, the carbon, the helium, eventually maybe even the hydrogen envelope, all of it falling inward, all of it crossing the event horizon, all of it gone from the observable universe. The elements that stellar nucleosynthesis spent millions of years building don't get distributed. They get swallowed. This matters for the chemical evolution of galaxies, actually. Not in a way that's catastrophic, because most of the nucleosynthesis happens in stars that do explode, and a lot of element production occurs in the stellar winds and outer layers that may escape even in failed explosions. But it matters. The universe's element budget is partly determined by the fraction of massive stars that explode versus collapse quietly, and we don't know that fraction precisely. There's a subtler version of failure worth mentioning because the binary of explodes/doesn't explode is a simplification. Some simulations produce what are called weak explosions. The shock revives barely and the star is partially disrupted, but the explosion energy is much lower than typical, and significant fallback accretion occurs after the initial ejection. The result might be a neutron star that's unusually massive, or a very faint supernova with low nickel production, or a transient that doesn't look quite like a standard core collapse event and gets classified oddly or missed entirely. The range of outcomes from core collapse is wider than the clean categories imply. It's not supernovae on one side and silent black holes on the other. There's a spectrum: faint supernovae, fallback supernovae, failed supernova, and probably things in between that don't have settled names yet. We are, in some sense, still learning what core collapse can produce. And here is the thing this chapter was always building toward, even though I've been approaching it sideways. The word explosion, which we've been examining from multiple angles since the beginning of this series, fails most completely not in the successful cases, where at least the outcome looks explosive, but in the failed ones. A core collapse event that produces no optical brightening, no ejector, no expanding nebula, where the entire energy of the gravitational collapse is carried away by neutrinos, and the remaining matter falls into a black hole. This is a supernova mechanism running in full without producing a supernova. The physics is identical in its early stages. The iron core, the Chandrasekhar limit, the infall, the nuclear bounce, the stalled shock, the neutrino flood. All of it happening in some star in some galaxy right now, probably. And ending not with a flash but with a black hole and a silence. Is the same machine, a different result, the threshold not crossed? I keep wondering, and I don't have an answer to this, whether the cases where the explosion succeeds tell us more about supernovae, or the cases where it fails do. The successful ones are easier to observe. We have thousands of light curves, thousands of spectra, decades of data, but they're just the outcomes where everything worked. Where the neutrino luminosity was sufficient, the convection was robust, the gain region tipped toward explosion. The failed ones are the edge cases, the places where the machine ran and the threshold wasn't reached. And those maybe are where the physics is most legible, where you can see exactly what was needed, because it wasn't there. A star that disappeared in NGC 6946 sometime around 2009, with no supernova to show for it. The machine ran. The threshold wasn't crossed. The galaxy has one fewer star and no good way to say why that particular one didn't make it, except that the numbers didn't work out, and the shock stayed stalled and the window closed before anything could push it open. The shockwave breaks through the stellar surface and the star begins to come apart. Not all at once. The inner layers, the processed core material, the nickel-rich ejector closest to the proto-neutron star are moving slower than the outer layers, which the shock accelerated to higher velocities because they're less dense. The whole thing is expanding, but it's expanding in a complicated way, with different layers at different velocities, mixing occurring at composition interfaces where Rayleigh-Taylor instabilities cause heavier material to finger into lighter material in ways that look, in simulations, like something between a breaking wave and a slow-motion ink drop in water. After a year, the remnant is light years across in some directions. After 1,000 years, it's a nebula. After tens of thousands of years, it's a faint, diffuse structure, still expanding, still sweeping up interstellar gas. cooling as it goes. The material is still there, changed but there. Let me just name some of what the shockwave made on its way out. In the innermost ejecta, where temperatures briefly reach 10 billion degrees during the shock's passage through the silicon shell, nickel-56, which decays to cobalt-56, which decays to iron-56. This is where most of the iron in a core collapse supernova comes from. Not all of it. Type 1 supernovae, the thermonuclear ones, produce more iron per event, but a meaningful fraction. The iron in the ejecta starts as nickel made in a few seconds of explosive silicon burning, and arrives at iron weeks later through radioactive decay. In the oxygen-burning shell, sulfur, argon, calcium, not in quantities that make headlines, but in quantities that matter to the elemental inventory of the galaxy over billions of years of star formation and death. In the carbon and neon shells, oxygen, neon, magnesium. Produced both during the star's hydrostatic burning phases and during the shock's explosive passage. In the outer helium and hydrogen shells, lighter elements, mostly unchanged from what the star had already accumulated, but now unbound, drifting outward at thousands of kilometers per second into whatever interstellar medium surrounds the explosion site. The R process is worth pausing on because it's genuinely not settled where it happens. The rapid neutron capture process, the mechanism that builds elements heavier than iron up to uranium and beyond, by adding neutrons to seed nuclei faster than beta decay can remove them, requires an extraordinary neutron flux. A neutron density so high that nuclei capture multiple neutrons in fractions of a second, building up isotopes far from stability before they have time to decay. The conditions for this are extreme even by stellar physics standards. Core collapse supernovae were long considered the primary R process site. The neutrino-driven wind off the proto-neutron star in the seconds after the explosion was thought to provide the right combination of neutron richness, temperature, and entropy. But the models have had difficulty actually producing the right conditions. The wind turns out to be proton-rich in many simulations, or insufficiently neutron-rich for the heaviest R process elements. Neutron star mergers, two neutron stars spiraling together and colliding, the kind of event detected as gravitational wave source GW170817, have now emerged as a confirmed R process site. The clonova that accompanied that merger showed clear signatures of heavy R process elements, including fairly certainly gold and platinum. Whether core collapse supernovae contribute significantly to the R process or not is still being worked out. Some simulations of particular explosion geometries, some special cases with rapidly rotating magnetized cores, do produce R process conditions. The answer is probably sometimes in some supernovae, in some mass range, the air process occurs. But it's not the clean story it seemed to be for a few decades. The gold in a ring might be from a neutron star merger, or it might be from a supernova, or both, mixed over billions of years of galactic chemical evolution. We don't have a way to distinguish them yet. What we can say with more confidence is this: almost every element in the periodic table heavier than helium has passed through the interior of at least one star. Hydrogen and helium are primordial, produced in the first few minutes after the Big Bang. Everything else, from lithium through uranium, has been processed in stellar interiors and distributed through stellar winds, planetary nebulae, and supernovae. Core collapse supernovae are particularly important for oxygen, the most abundant element in the universe by mass after hydrogen and helium, and for the alpha elements neon, magnesium, silicon, sulfur, argon, calcium. These are produced in massive stars and distributed when they explode. The ratio of alpha elements to iron in old stars is used as a chemical clock, telling us something about the star formation history of a galaxy based on how many core collapse supernovae had occurred before the star formed compared to how many Type 1a supernovae. The elements are not just products, they're records. The kettle I boiled earlier left a small calcium deposit on the inside, visible as a faint white ring. Hard water, the usual explanation. The calcium in that deposit was synthesized in the oxygen-burning shell of a massive star that exploded before the solar system formed, drifted through the interstellar medium for some millions of years, was incorporated into the molecular cloud that collapsed to form the Sun and planets 4.6 billion years ago, ended up in the oceans, entered the water supply, came out of my tap, and is now sitting in my kettle. That's not a metaphor, that's the actual provenance. The chain is real, every step of it. The neutron star or black hole left at the centre of all this. It's easy to treat the remnant as a postscript, the thing left over after the interesting part, and I've been guilty of that framing throughout these chapters. But the object that forms at the centre of a core collapse supernova is its own ongoing physics problem, not a conclusion. A neutron star is roughly 20 kilometers in diameter. It contains between 1.2 and 2 solar masses of material compressed to nuclear density. It has a solid crust of neutron-rich nuclei, a liquid interior of superfluid neutrons and superconducting protons, and possibly, depending on density and temperature, exotic phases of matter in the innermost core that we genuinely do not know how to describe with certainty. Strange quark matter, color superconducting phases. The equation of state of neutron star matter at these densities is one of the outstanding problems in nuclear physics. The neutron star rotates, sometimes slowly, sometimes hundreds of times per second, depending on the angular momentum of the progenitor core. It has a magnetic field, sometimes extraordinarily strong, 10 to the 12th Gauss for typical pulsars, 10 to the 15th Gauss for megatars. It emits radiation from its magnetic poles, and if those poles are misaligned with the rotation axis, the emission sweeps across space like a lighthouse beam. It cools over thousands of years from hundreds of billions of degrees to millions, eventually to the point where the cooling is primarily neutrino emission from the interior rather than photon emission from the surface. It persists, in some cases, for billions of years. The supernova was not the end of this object. It was the beginning. The star that burned for millions of years, the massive, luminous, hydrogen-fusing thing that produced iron in its core and silicon in its shells, was the preamble to a neutron star. The entire stellar life, all that burning and processing and shell development, was building toward the conditions that produced the collapse that produced this object, which will now sit in the galaxy for longer than the original star lived, spinning, cooling, occasionally being detected by a radio telescope as a millisecond pulsar if it's been recycled by accretion in a binary system, or as an X-ray source if it's still accreting, or not detected at all if it's isolated and cold. The star that exploded is gone. The thing it became is not. The ejector, expanding outward over millions of years, will eventually be incorporated into new molecular clouds. The oxygen and magnesium and calcium and iron will mix with primordial hydrogen and helium and the processed material from other stars, and eventually, given the right conditions, a perturbation, a compression wave from another supernova, or a galactic density wave passing through, the cloud will collapse. New stars will form. Some of them will have planets. The planets will accrete material that includes everything the original supernova made. The oxygen dissolved in the oceans of such a planet, the calcium in its rocks, the iron in its core, the sulfur in its crust, all of it traceable in principle to the nuclear burning in a star that died billions of years earlier. And if something like life arises on such a planet, if, through whatever processes chemistry undergoes over long timescales in warm water near an energy source, self-replicating molecules form and eventually become cells and eventually become something more complicated, then the iron in whatever passes for blood in such a creature was made in the oxygen-burning shell of a star, carried outward by a shockwave, drifted through space, collapsed into a new solar system, and arrived. Not as a metaphor, as iron. I said at the beginning of this chapter so that the material was changed but still there. That's what I meant. The star is gone. The neutron star persists. The ejector drifts. The elements travel. And somewhere, not just metaphorically, not just poetically, but physically, measurably, in the specific atoms of the specific molecules of the specific cells, doing the specific work of keeping a body running right now. The star is still here. What a supernova leaves behind is not an absence. It's everything it ever was, redistributed. Explosion, it's a good word. Short, physical, unambiguous in almost every context where it gets used. Something compressed releases its energy faster than the surrounding material can respond, and the result is an outward motion, rapid, violent, irreversible. Gunpowder, a gas main, a pressure vessel. The word carries its meaning efficiently, and it's been doing this work for a long time. We applied it to supernovae, and it mostly fit from the outside. The star brightens. The material moves outward. The velocities are enormous. The energy released dwarfs anything else in the stellar catalogue. If you wanted a single word for what a supernova looks like from a distance, across a galaxy, through a telescope, explosion is not wrong. It just doesn't describe what happened. What happened, as best we understand it, is this. A star's iron core accumulated past a threshold determined by quantum mechanics and gravity. Electron degeneracy pressure failed. The core collapsed inward in roughly 100 milliseconds, reaching nuclear density, bouncing. A shockwave formed and immediately began losing energy to the iron it was trying to push through. The shockwave stalled. For up to a second, the system sat in a marginal state on turbulent, asymmetric churning, while neutrinos from the proto-neutron star deposited energy in a thin shell of material behind the stalled front. The shock revived unevenly in some directions before others. It climbed through the stellar layers for hours. It broke through the surface. The envelope expanded. Radioactive nickel decayed and lit the ejector from inside over the following weeks. The light arrived at telescopes. We called it an explosion. The sequence laid out like that doesn't feel like an explosion. It feels like a threshold, a stall, a marginal revival, and a very long propagation followed by an afterglow, which is more accurate. But also harder to say at a dinner table when someone asks what a supernova is. I'm not making a case for replacing the word. That's not what this chapter is doing. Words are tools, and exclusion does real work in the context of supernovae. It correctly conveys scale, energy, irreversibility, outward motion. A core collapse supernova is genuinely one of the most energetic events in the observable universe. Calling it an explosion isn't wrong the way calling the Earth flat is wrong. It's wrong the way a map is wrong. Useful, functional, not the territory. The territory is a gravitational implosion that produces a bounce that produces a stalled pressure wave that gets revived by a particle so weakly interacting it passes through lead for a light year. The territory is 99% of the energy leaving the star invisibly, in particles we can't feel, carrying heat from a nuclear flaw that matter hit at a fifth of the speed of light. The territory is a shockwave that almost didn't make it, in a star that for some fraction of similar stars doesn't make it, the outcome depending on conditions in a shell of plasma 100 kilometers across in the middle of a star millions of kilometers wide. The territory is messier than the word, more contingent, more dependent on physics that operates at scales we've never touched and may never touch. More interesting, honestly, than an explosion, because an explosion is a known thing, a category of events we have extensive experience with, a phenomenon with clear mechanics. What a supernova actually is hasn't had a clean word for it yet, and maybe doesn't need one. Outside there's a low fog settled over the street. I can see it through the window. The streetlight has a diffuse halo around it, the kind that happens when the air is carrying moisture and the light scatters before it reaches you. The actual source of the light is clear. What arrives at the eye is blurred, spread, a version of the original processed by what's between. I find myself thinking about that, about all the information that travels through something before it gets to you and what it looks like when it arrives. Here is what I've been thinking about throughout these chapters that I haven't said directly. We built our understanding of supernovae mostly from the light, from the afterglow, from the spectral lines of expanding ejecta, the light curves of radioactive decay, the faint remnants still glowing thousands of years later. This is not a criticism. It's a remarkable scientific achievement, extracting as much as we have from downstream signals. But it means that the most important part of the event, the collapse, the bounce, the neutrino flood, the revival, was invisible to us for most of the history of astronomy. We named the event after its least energetically significant component, the light, the 1%, and the name stuck. And it's fine that it stayed stuck, because the light is real, and it carries real information, and it's genuinely extraordinary. But somewhere in calling it an explosion, in centering the optical brightness, the visible outward motion, we may have built an intuition about supernovae that points slightly away from what they are. They are not stars that explode, they are stars that collapse, and sometimes, if the conditions are right, the collapse produces an explosion. The distinction sounds pedantic. I don't think it is. The collapse is the mechanism. The explosion is the outcome of a mechanism that can fail. If you think of supernovae as explosions, the question is, what triggered the explosion? If you think of them as collapses, the question becomes, what conditions allow the collapse to produce an outward-moving shock that successfully revives and disrupts the star? The second question is the one astrophysicists are actually working on. 25 neutrinos in a water tank in Ohio in February 1987, hours before the light arrived. That's the most direct observation we have of a supernova mechanism. Not the explosion, but the collapse, the neutrino flood, the proto-neutron star cooling, 25 particles from 10 to the power of 58. Detected because someone built a large tank of very pure water and watched it for other reasons, and a star happened to die close enough for a few of the neutrinos to interact. The light from SN 1987A was spectacular. It was visible to the naked eye from the southern hemisphere for months. Astronomers pointed every available telescope at it. We learned an enormous amount from the light. But the neutrinos came first. The neutrinos were the event. The light was the evidence that the event had occurred. So, explosion. We'll keep using it. It's not going anywhere, and there's no competing word that does the job better in casual usage. When a massive star ends its life in a core collapse supernova, explosion conveys something true about the outcome, even if it misses almost everything about the mechanism. But maybe, and this is all I'm really suggesting at this hour, at the end of this particular journey through the physics, maybe the word is a starting point rather than a description. A placeholder that points towards something the language hasn't fully named yet. A star collapses. The collapse almost fails to produce an explosion every time in every massive star that ends this way. The explosion happens because a thin shell of plasma absorbs 1% of a neutrino flood and tips a stalled pressure wave back into motion. That's not an explosion in the way the word usually works. It's something stranger, something that required 11 chapters to approach and still feels, at the edges, like it hasn't been quite said. The universe didn't consult the word before doing what it just did it. Indifferently or repeatedly, across billions of years and hundreds of billions of galaxies, and we watched the light and named it. On the night of February 23rd, 1987, a Canadian astronomer named Ian Shelton was working at Las Campanas Observatory in Chile, reducing photographic plates from a survey of the Large Magellanic Cloud. Routine work, the kind of work that accumulates over years into a body of data that occasionally, rarely, means something unexpected. He noticed a bright spot on one of the plates that hadn't been there the night before. He went outside and looked up. It was visible with the naked eye. A star, or what appeared to be a star, in the large Magellanic Cloud, the small irregular galaxy that orbits the Milky Way at a distance of roughly 160,000 light-years. Magnitude 4.5 when he first saw it, brightening, where there had been the previous night an unremarkable blue star catalogued as Sanderleak minus 69 degrees 202. The star had been known. That's the part that still strikes me as remarkable when I think about it. Not discovered in the explosion, known beforehand, catalogued, sitting in archives, photographed repeatedly as part of survey work. Sanderleak minus 69 degrees 202 was a blue supergiant, roughly 20 solar masses, and it had been documented for years without anyone having particular reason to watch it closely. Blue supergiant, not red. This matters, because the theoretical expectation at the time was that core collapse supernovae should come from red supergiants, larger, more extended, cooler. Red supergiants had been observationally associated with supernova remnants. The stellar evolution models pointed toward them. A blue supergiant wasn't supposed to be the right kind of star. SN 1987. A was the right kind of event from the wrong kind of star, and the wrongness turned out to be one of the more instructive aspects of it. It forced a reconsideration of which stars explode and when in their evolution. It suggested the progenitor had been a red supergiant earlier and had contracted, evolved back toward hotter temperatures before the core collapsed. The stellar evolution models had to absorb this. Some of them still haven't fully reconciled it. The light arrived at Earth on February 23rd. The brightening was observed that night. The neutrinos had arrived several hours earlier. This is the sequence that matters, not as a dramatic detail, but as a physical confirmation of everything the theory had been building toward for 20 years. The core collapses. Neutrinos leave immediately, at very nearly the speed of light, carrying 99% of the gravitational binding energy. The shockwave takes hours to reach the stellar surface the light leaves when the shockwave breaks through. So the neutrinos produced at the moment of core bounce left the star hours before the optical photons did. They travelled 160,000 light-years. They arrived at Earth, passing through it mostly as neutrinos do, and a handful of them, against all probability, interacted with water molecules in 3 underground detectors. Kamiokanda 2 was buried under Mount Kamioka in Japan, inside a zinc mine. It was a tank containing 3,000 tons of ultra-pure water, surrounded by about 1,000 photomultiplier tubes watching for faint flashes of Cherenkov radiation. It had been built to search for proton decay, a predicted but unobserved phenomenon from grand unified theories. It wasn't built for supernova neutrinos, it was looking for something else, running continuously, accumulating data. At 7:35 am Universal Time on February 23, 1987, it recorded 11 events in a 13-second window. IMB, the Irvine, Michigan Brookhaven detector, a water Cherenkov detector in a salt mine in Ohio, 8,000 tons of water, also built for proton decay, recorded 8 events in roughly the same window. Baksan in Russia recorded 5, 24 events, 24 neutrinos interacting with water in 3 separate detectors on 3 different continents in a 13-second window hours before the optical brightening was observed. There's a moment I keep returning to, not in 1987, but in the months after, when the data from the 3 detectors was being compared and the timing was being checked and the energies were being measured. The neutrinos had energies of roughly 10 to 40 mega electron volts. The burst lasted about 13 seconds, The total energy implied by even this tiny detected fraction, extrapolated to the full isotropic emission, was consistent with the gravitational binding energy of a neutron star, roughly 3 times 10 to the 53rd power ergs. The theory had predicted this number, had been predicting it since the 1960s, and here it was, confirmed not by observing the explosion, not by the light curve or the spectral lines or the expanding nebula, but by 24 particles that had barely interacted with anything on their 160,000 light-year journey, and had almost not interacted with the detectors either. 24 data points confirming a mechanism that had been theoretical for 2 decades. I've been sitting at this desk long enough tonight that my lower back has started its usual complaints, that particular tight ache that develops somewhere around the 2-hour mark. I notice it and set it aside. Some things are worth sitting through. The 3-hour gap between the neutrino burst and the optical detection is worth dwelling on, because it's not just a sequence, it's a measurement. It tells us that the shockwave took several hours to cross from the core to the surface of Sanderleak minus 69 degrees 202, which gives us information about the stellar radius, which is consistent, given the blue supergiant classification, with its more compact structure compared to a red supergiant, with what the pre-explosion images told us about the star. The neutrino timing, the optical timing, the progenitor images, the light curve, the spectral evolution, all of it, from an event 160,000 light-years away, assembling into a coherent picture. This is what physics looks like when it works. Not elegant, messy, multi-instrument, requiring observations that were made for entirely different purposes by people who didn't know they'd need them, but coherent. The pieces fit. SN at 1987. A is still being observed. The remnant is expanding. The shockwave from the explosion has been colliding with a ring of material that the progenitor ejected thousands of years before the collapse, when it was still in an earlier evolutionary phase, and the collision has been lighting up that ring in X-rays and radio waves in ways that have provided a detailed probe of both the explosion geometry and the progenitor's mass loss history. Hubble has photographed it repeatedly over 3 decades. The ring has been brightening, then evolving, the collision dynamics playing out on human timescales because the ring is close enough and the geometry is favourable. The neutron star, which should be there at the centre, the remnant of the collapsed core, has been frustratingly hard to confirm. There have been hints, a point source detected in X-rays and infrared by recent observations that is consistent with a young, hot neutron star still surrounded by dust. But a clean direct detection has been elusive. It should be there. The physics says it should be there. Finding it conclusively, extracting its properties, would add one more confirmed piece to the picture. We're still looking. What SN 1987A gave us, more than any specific measurement, was a proof of concept. The neutrino mechanism, the idea that core collapse supernovae are driven by neutrino energy deposited behind a stalled shock, had been theoretical since Colgate and White in the 1960s. The simulations had been building the case for it. The theory was considered probably correct, but probably correct and confirmed by observation are different things, and in astrophysics the distance between them can be very long. 24 neutrino events closed most of that distance, not all of it. The revival mechanisms, the detailed physics of how the stalled shock gets pushed back into motion, is still being worked out, as we've discussed. The simulations are still improving. The role of turbulence and SASI and progenitor asymmetry is still being quantified, but the basic picture, collapse, neutron star formation, enormous neutrino burst, some fraction of that energy driving the explosion, is now observationally anchored. SN 1987. A is the anchor. I find myself wondering occasionally about the timing, not cosmically. I don't mean anything mystical by it, just practically. Kamiokande 2 had been running for about 2 years when SN 1987A occurred. IMB had been running longer. Both had been built for proton decay, which hasn't been observed and may not be observable with any realistic detector. In one sense, they failed at what they were built for. In another sense, they were running underground, full of pure water, waiting without knowing they were waiting for a star 160,000 light-years away to collapse. The Large Magellanic Cloud was visible from the southern hemisphere. Chile had observatories. Someone was reducing plates that night, doing routine work, and went outside. The confluence of these things, the running detectors, the southern observatory, the clear night, the decision to go outside and look, is the kind of thing that resists analysis, not miraculous, just contingent, the way science usually is. A lot of people doing their work, and occasionally the work intersects with something the universe was doing anyway, and something is learned that couldn't have been learned otherwise. The neutrinos from SN 1987A have been travelling since February 23, 1987. The ones that didn't interact with the detectors, the vast majority, the 10 to the power of 58 minus 24, continued outward. They are still travelling. A sphere of neutrinos, 37 light-years in radius now, expanding at the speed of light, carrying with them the energy signature of a stellar core that collapsed on a specific day and produced a specific neutron star in a specific galaxy. They will continue outward for billions of years. They will pass through other galaxies. Some tiny fraction of them will interact with something somewhere and deposit a small amount of energy. Most will travel indefinitely, cooling as the universe expands, becoming part of the diffuse background of relic neutrinos that permeates all of space. The event is over. The evidence is still moving. And on Earth, in 3 underground tanks of water, on a single night in February, 24 of them left a mark that confirmed something physicists had been working toward for 2 decades. 24 out of 10 to the power of 58. It was enough. Somewhere in the observable universe right now, a massive star is crossing the Chandrasekhar limit. Not metaphorically, not as a way of gesturing at cosmic scale. Right now, in the time it takes to read this sentence, in some galaxy among the 2 trillion estimated to exist in the observable universe, an iron core has accumulated past the threshold, and the electrons have stopped being enough and the infall has begun. This is not a rare event. It only feels rare because we're looking from one small point in one ordinary galaxy, and our telescopes, for all their reach, sample an almost negligibly thin slice of what's out there. The universe is running this process continuously the way the atmosphere runs weather, not occasionally, not memorably, just constantly in the background, without waiting for anyone to be watching. The numbers are rough, because they have to be. We're estimating across distances and timescales where precision is hard won. But the broad figures are these. A galaxy like the Milky Way produces roughly 1 to 3 core collapse supernovae per century. The observable universe contains something like 2 trillion galaxies. Even accounting for the fact that most of those galaxies are smaller and less star-forming than the Milky Way, the rate across the observable universe works out to something in the range of hundreds of core collapses per second. Per second. The last confirmed supernova in the Milky Way visible to the naked eye was Kepler's supernova in 1604. 4 centuries of violence in our galaxy. while the universe outside it has been producing these events at a rate that makes silence feel like a peculiarity of our location rather than a property of the phenomenon. Most of them we will never see, not because our telescopes aren't powerful enough, many are detectable in principle across billions of light years, but because the universe is large enough that even hundreds of events per second, distributed across 2 trillion galaxies spread across 93 billion light years of observable space, amounts to a very thin signal per unit of sky. We catch a few hundred per year in dedicated surveys. We miss incomparably more. The ones we miss aren't less real. The iron cores crossed the threshold. The bounces happened. The shockwaves stalled and some revived and some didn't. The neutrino floods happened, carrying their 99% out into intergalactic space, undetected, undetectable with current technology, joining the diffuse background of relic neutrinos that fills all of space with the warmth too faint to measure. The elements were made or not made, depending on whether the explosion succeeded. The neutron stars formed, or the black holes formed, quietly, in galaxies too far away to examine individually. All of it happening right now while this sentence is being read. There's an accumulated consequence to this rate that's worth sitting with briefly. Over the roughly 13.8 billion years of cosmic history, across the star formation that's been ongoing since the first population 3 stars ignited a few hundred million years after the Big Bang, the total number of core collapse supernovae in the observable universe is estimated in the range of 10 to the 23rd power, 100 sextillion events, each one processing stellar material, distributing elements, energizing the interstellar medium, forming neutron stars or black holes, contributing to the chemical evolution of its host galaxy. The oxygen in Earth's atmosphere, all of it, is the cumulative product of stellar nucleosynthesis distributed by events like this over billions of years in stars that lived and died before the solar system formed. The calcium in bone, the iron in blood, wherever it came from, supernova or neutron star merger or some combination of both. The silicon in rock, the sulfur in protein, the phosphorus in DNA. The universe has been running this process for nearly its entire history, and the material it's produced is what everything is made of. My coffee went cold about an hour ago. It's sitting at the edge of the desk, unremarked upon until now. Ceramic mug, dark interior, the surface of the coffee perfectly still in the way that cold liquid is still, without the faint convection currents that warm liquid has. There's iron in the ceramic, there's calcium, there's oxygen in the water that brewed it, in the coffee itself, in the air above it. All of it here, in this room at this hour, because stars died at rates of hundreds per second across billions of years and distributed what they had. It's not a metaphor, it's inventory. The word extone, which we've been living with since the title of this series, does something interesting when you hold it against this rate. Explosions in ordinary experience are events, discrete, bounded, memorable. They have a before and after, they mark time. Even large-scale explosions, volcanic eruptions, nuclear tests, are events in a way that allows you to point to them on a timeline and say, there. Core collapses at the rate the universe runs them are not events in that sense. They are a process, continuous background. The way erosion is a process, or radioactive decay, or the hydrogen burning in the cores of the 100 billion stars in this galaxy alone. Something that is always happening somewhere that changes the state of things gradually and irreversibly, and that we only notice locally when geometry puts one close enough to see. The word explosion was coined for events, What the universe is doing is something more like a condition, which doesn't mean any individual core collapse isn't dramatic in the physics. We've spent 13 chapters on the drama of one: the ion accumulation, the infall, the nuclear flaw, the bounce, the stall, the neutrino flood, the revival, the propagation, the light. Each one of those things happening in each individual star is extraordinary by any measure. But the extraordinariness doesn't require rarity. A thing can be physically extraordinary and cosmically routine simultaneously. Those aren't contradictions, they're just different scales of description. The universe doesn't reserve its physics for special occasions. It runs the same processes in every massive star that reaches the end of its silicon burning, in every galaxy at every redshift across all the time we can observe, and most of it goes unwitnessed, and all of it leaves the universe slightly different than it was before. I want to say something near the end of this that I've been approaching from several directions without quite landing on. There's a tendency, understandable, maybe inevitable, to treat cosmic events as being about us, to frame the elements in our bodies as the universe's gift, to describe supernovae as the factories that made life possible, as though the stars were doing something for something. The language of purpose creeps in because human minds find purpose easier to hold than indifference. But what the rate of core collapses suggests, hundreds per second across 2 trillion galaxies ongoing for nearly 14 billion years, is something more simply stated. The universe produces massive stars. Massive stars exhaust their fuel. Physics takes over. The outcomes vary, but the process doesn't stop. It runs in the background of cosmic history, the way weather runs in the background of a day. Not for anything, not building toward anything, just the operation of forces on matter over time. The fact that some of the output ended up as ozone and blood, and the particular arrangement of carbon that reads these words, that's real. That's not diminished by the indifference. If anything, it's stranger for it. Not a gift. Just what happened to some of the material. Somewhere in the observable universe right now, a shockwave that stalled 300 milliseconds ago is beginning to revive. The gain region behind it has been heated past the critical threshold. The neutrino luminosity from the proto-neutron star below has been sufficient, barely, and the turbulence has been favourable, and the shock is starting to move outward through material it hasn't crossed yet. In a few hours it will reach the stellar surface, in a few days the light will peak, in a few weeks it will fade, in a few thousand years it will be a nebula. In a few million years the material will be incorporated into new molecular clouds. No one in this galaxy will see it. The galaxy it's in is too far, the event too faint at this distance, the sky too full of other things demanding attention. It will happen anyway, completely, correctly. Every step of the physics running as it runs, the same way it ran in the star we've been describing for 14 chapters, the same way it will run in the next massive star in the next galaxy, to cross the threshold. The word we used for it was explosion. What it actually is, this slow collapse, this stalled wave, this neutrino tide, this hours-long climb toward a surface that doesn't know what's coming, doesn't have a cleaner word yet. Maybe it doesn't need one. The universe has been doing it without a name for nearly 14 billion years, and it will keep doing it long after whatever words we have for it have been forgotten, in galaxies so far from here that even the light from tonight won't have reached them yet. Still happening. Right now, somewhere. This project is self-funded, a team of 3 making something we hope is worth your time, with no algorithm deciding what it becomes. If these long, slow journeys through physics are something you find yourself coming back to, the best way to help keep them going is on Patreon. The link is in the description. Matthew M. and Brian Winter, your support has been a genuine foundation for this work, and I mean that more than the usual way people mean it. Alison, you've been here longer than almost anyone, and that kind of quiet, sustained presence is its own extraordinary thing. To every other Patreon member who shows up for this, thank you, not in a closing credits way, in the way that actually means something at the end of a long night when the work is done. If you're not on Patreon but want to be, it keeps this going. That's all it does, and that's enough.